In this video, and the next video, we're going to look at 5 ways to define a new function by combining two existing functions. In this first section, we're looking at operations on functions. I think you'll find this is a very intuitive idea, where we take two functions and combine them using the traditional operations of addition, subtraction, multiplication, and division. So we're going to give an example and the definition at the same time. So here's the two functions we're going to use as our example. Let's let f of x be the square root of x and g of x be the function x cubed. We can take these two functions, which we know a lot about, and combine them together. So on the left, you'll see the definition and some notation. Remember, notation is just a way to write something. So this is a way to write these kinds of functions. And then on the right, we're going to fill in what this new function would be using our f of x and g of x at the top. Okay, so I think you can see this column on the left. I guess I didn't put the names in this, but the first one is called the sum function because we're creating a new function by adding these two functions together. And you can see here this is the new name of the function, right? F plus g of x. But intuitively, it's exactly what you would expect, right? This is just the sum of f of x and g of x. Same thing's true here. So now we're going to use our two example functions, and we're going to add them together to make a new function. The square root of x plus x cubed. Okay, and then we could do that for really all 4 operations. So we have f of x minus g of x. This would be the difference function. And it's calculated by subtracting f of x minus g of x. For our particular example, that would be the square root of x minus x cubed. Okay, and then we have the product function where we multiply. This little dot here indicates multiplication. So we're just going to multiply f of x and g of x. So for our example, we're going to multiply the square root of x times x cubed. Generally, if you multiply with a square root, I'm going to reverse the order just to make it look nicer, but we're still multiplying, and we are always allowed to multiply in any order. Okay, and then the last function is the quotient function, where we divide f of x divided by g of x. Anytime we do division, right, we want to make absolute sure that we're not dividing by 0. So we have the little addendum here that says, okay, I can do this as long as g of x is not equal to 0. Okay, so for our particular example, this means we have the square root of x divided by x cubed. Now we should probably stop for a second and just talk about the domain for these functions, right? So in order to create a new function, the domain, let's just take the first one for this new function, needs to have x values that will work in both, right? So the domain for the square root of x, I'll just pencil it in underneath. We've talked about this quite a bit, right? I can't take the square root of something negative, but anything 0 or bigger, 0 or positive numbers will work. We've said that perfect squares are convenient, but they aren't a requirement. Any positive number I can take the square root of. For g of x, the domain of x cubed, I don't really have any problems here. I don't have any numbers that I can't raise to the 3rd power. So all real numbers would be the domain for this one. So if we look at the overlap between these two sets of numbers, right, this domain contains every number. This domain contains only 0 and positive numbers. The numbers that they have in common, right, would be anything 0 and bigger. So when I go to make this function and I add these two together, it would not be appropriate to put in an undefined a negative number for x. Because if I did put a negative number for x, I wouldn't be able to calculate the square root part of this function. I could do the x cubed, but not the square root. So the domain for actually all three of these first ones here would be from 0 to infinity. So the overlap. I need to use numbers that work in both. Same thing if I make the difference function. Same thing if I make the product function. The quotient function, remember, has this extra caveat. I don't want the denominator to be 0. The only way the denominator of this function could be 0 is if x is 0. So I don't want x to be 0. Probably should have written that here earlier. Okay, so in that case, the domain would be all the numbers that would work for both, except for that one number that would make the denominator 0. In this case, that is 0 itself. So when I write the domain for the quotient function, I'm going to leave out the number 0 itself and use the round parentheses. Okay. So there are a few common examples that we can talk about that make use of this kind of new way to make a function. Two of the most applied examples use the idea of revenue, cost, and profit. So let me just take a second to talk about those with you. So revenue would be these are kind of business-based examples. Revenue would be the money a business receives from sales of goods or services. So I find it easier to think of myself as the business owner when I do these problems. So if I own a business, revenue is money I'm bringing in when I sell my product, or maybe it's a service when I do my service, right? It's the money I'm bringing in. And then the cost is the money a business spends in order to produce and sell. So this could be two kinds of costs. This could be variable cost, things that I have to buy per item I'm producing, or fixed costs. So as the business owner, let's say, for example, my mom wanted to make a business at one time that would make wedding veils and sell them. Okay, so the revenue would be the money she would earn. Hopefully she could sell a wedding veil for $100, $200, something like that. So she would bring that money in. The cost would be the money that she had to spend on materials. If she had employees, she would have to pay her employees. So the materials would fall into the category of the variable costs because she would be paying them per item, per wedding veil. The fixed cost would be things like electricity, or if she had a physical location like a building that she was renting, things that she had to pay one time as a business, maybe regularly, but not depending necessarily on how many wedding veils she produced, right? So both of those types of costs, think of yourself as the business owner, would go into the cost function. And then the profit would be money gained above expenditures. So hopefully the money I bring in is more than the money I have to pay in costs. And so any of that money that's left over once I pay my bills, right, would be the profit. Okay, so we can take this idea and join these two ideas together. So here's an example that uses these three. So let's say we have a company that produces and sells TV sets. We have a function here that describes their weekly cost and their weekly revenue. So this $54.60 would be the fixed cost. This is the cost that I have to pay every week, whether I produce TV sets or not. This would be the variable cost. Notice it's multiplied by X. I don't think I wrote that here, but X in this case would be the number of TVs. Okay, so for each TV I produce as the business owner, I would have to pay $189 in materials or labor or something like that. Okay, and then I have the revenue function. This is the money I'm bringing in. Usually this number in front of X is the price of the item that I'm selling. So I'm selling these TVs at $988 per TV. And I can put in how many TVs I sell and then calculate how much money I'm bringing in total. Okay, so the question is, what is the weekly profit if 80 TVs are produced and sold? So we said the profit, we'll use big P of X here for profit, is the money I bring in, the revenue, minus the costs, bills that I have to pay. So I could take the two functions that I have and create a new one. So I have 988x for my revenue, and then I'm going to subtract the cost. Since the cost has more than one term, I'm going to put it in parentheses. And then I can distribute my negative sign. And I can combine like terms. 988 minus 189. If this were 188, it would be 800, but it's less than that. So it should come out to 799x. Okay, and then I would, I'm asked specifically, so here's my function, and then I'm asked specifically, what is the weekly profit if 80 TVs are produced and sold? So I would want to plug in 80 for X. And calculate what that is. And so we could put that into our calculator. Okay, and calculate what that is. So let me do that. I didn't bring my calculator in here with me, so let me see if I can calculate this. You probably could already have punched it into your own calculator at this point, and maybe you have, so let's check if we get the same answer. Alright, I'm not having a lot of luck with this. There we go. going to leave that blank right now because I don't have my calculator on me. Maybe we'll come back in a second and fill that in. Okay, let's move on. The next question is, what is the average cost to produce 80 TVs in a week? So the average cost breaks up the total cost that we're paying, in this case it's per week, per TV, right? This is a company that produces and sells TVs, so we're going to take the cost and break it out and divide it up between each TV. So the average cost is usually written as a C with a little bar over it of X. And that takes the total cost and divides it by X. So if we go back up to the top, all right, here's our total cost, 189X plus 5460. So we can make our new function as 189X plus 5460 divided by X. Okay, and we could do the same thing here. We could plug in the average cost of 80 TVs. So this would take the cost for 80 TVs. And break it up for each TV. Let's see if I can calculate that one a little easier. Let me try that. I got 20,580 over 80. And so if I divide that, it looks like I get $257.25. Okay, and this is per TV. So if you look back up at the top, right, the revenue function said that we're selling these TVs for $988. And this is how much it's actually costing us as the business owner. So we're making a pretty good profit here for each TV. I hope that you can see that. All right. So we have two other places where we can apply this idea of combining functions. These are a little bit more abstract applications. So I want to look at them both with you one at a time. The first one is the average rate of change. So the average rate of change is basically the same idea as slope. But we're kind of extending the idea of slope so that we can try to approximate the slope of a curve. We are just sort of taking a little step in this direction when we talk about this idea, and the next one, calculus, is really where you start to get serious about calculating the slope of a curve. We're just going to give you a little bit of information about this, but I want to tell you what it's based on. Okay, so the average rate of change is basically the slope formula, but we're subtracting. We use the function notation. So really this is the y value when I use b as my x, and this is the y value when I use a as my x. It's a lot like y2 minus y1 over x2 minus x1. It's just written in a little bit different way. Okay, so the average rate of change, what it does is it calculates the slope of a special line called the secant line. And the secant line is a line joining 2 points on a graph. So I can look at the graph that's a curve, choose 2 points, and calculate the slope of the line between those 2 points. So here's an example that the book gives, and so I want to work that example with you. And then this is not my favorite example, but I'm going to go with it. So then we can talk about why it's maybe not the best example, and maybe we can work an extra, fit in an extra calculation at the end here. Okay, so this is an example that comes from, it may not be your book, but it comes from a book. It says, for the function shown in the figure, find the average rate of change from -1, 2 to 2, -4. So notice I've already taken the time to draw the secant line that joins those 2 points on this curve. It's a parabola curve that opens down, right? And these are 2 points on that curve. And so I drew the line through them. What the average rate of change does is it finds the slope of that line. We've found the slope of many lines already. So the skill here is really not any different than that. I'm going to abbreviate average rate of change so I don't have to write that out. Okay. So essentially I'm just going to use the slope formula. The y2 minus y1 over x2 minus x1. So in this case, I'll make this the second point and the first point. So I'll do -4 minus 2 over 2 minus -1. And that's going to give me -6 over +3. So the average rate of change here is -2. And I get an actual number for the average rate of change. It is a slope of a line. So I get, this is my final answer. Right? Okay. Now, can we talk for a second about why I don't really like this particular example? So usually the point of this is to choose a secant line that sort of hugs really close to the curve so that when you find the slope of the line, you're getting an approximation for the slope of the curve. Since this secant line is nowhere near the curve, it's not even on the same side of the curve, I really don't feel like this is the best example, but it does give you an idea of the process. So how could we change it maybe? This point is really not that close to this point, but this point has a mirror image point right here at +1, 2. So can we sort of add a part B here to this problem? So these 2 points, I mean, they're not super close, but they're fairly close. We could draw a secant line between them. Let me see if I can use this piece of paper as a straight edge. Okay, I don't even know if you can see that because it's really close, to the curve. If we were to blow it up, let me do that down here. If we were to blow it up, here's our 2 points, right? We have the curve, and then we have the secant line that is not curved, it's straight. So I'll put the arrows on the secant line, okay? So we have the secant line, and it's very close to this curve. So by calculating the slope of the line, I'm in a sense calculating an average for the slope of the curve kind of in between these 2 points. Let me label it. Okay, so that gives it maybe a little more context than the first original example. We could do it, the calculation though, the same way. The average rate of change, we use the slope formula, so we'll do y2 minus y1 over x2 minus x1 I get negative 6 over 1, or negative 6. Okay, and this is sort of like a part B. This is maybe part A, okay, because we changed the question a little for part B. Okay, so hopefully you can see the basic idea here, right? I'm finding the slope of a line that is hugged close to the curve. Okay, so this is the average rate of change. There's another idea that's very similar to this that takes it one step further. It's not as specific with the points that we have here. It's a little bit more general, and in this case we will sometimes find a formula that we can use to calculate the slope of the line. So let's talk about the next idea. This is called the difference quotient. Okay, so the difference quotient is the average rate of change between 2 points that are very close together. So we have x and x plus a really small number. So if you think of, let me see if I can draw you a picture. Think of x, and then right next to it being x plus h. Oops, x plus h, it's an h. And we have some kind of a curve, and so we're taking the 2 points, just like we did the 2 points on the curve on the last example, we're taking these 2 points really close together. We could make h be a really tiny number like 0.01. So they're really, really close. And then use the idea behind the average rate of change. But we're going to do it this time in a little more general way with variables. Okay, so the difference quotient is us calculating the average rate of change with these two x values. So it's still the same, y2 minus y1 over x2 minus x1. We're using that function notation again. So this is sort of like our y2, and this is sort of like our y1. And then x plus h is x2, and x is x1. Okay, so that's how we form the difference quotient. Notice in the bottom we have a positive 8x and a negative x. So those actually are going to subtract away and cancel each other out. So our final, once we've done that, our final formula actually looks like this. F of x plus h minus f of x all over h. I will give you this formula. You do not need to memorize it. You only need to know how to use it. Okay, and we're going to use this formula on a specific type of problem just to keep it simple so that you know what to expect and you can focus on performing the steps. If you're going on to pre-calculus, you will spend a lot of time calculating the difference quotient because this is sort of a preliminary step to finding the derivative in calculus. Okay, but in our class, I like to limit it just to functions that are linear so that you can get a good idea of how this works. Okay, if you wanted to break this up into steps, you could first start by finding the f of h part. And then once you've found that, you can put it together with the regular function, which you already have, and then finally divide it by h. So calculating f of x plus h is really just amounts to substituting x plus h into the original formula for the function. So in place of the x, right here, all in one spot together, I'm going to put in parentheses, x plus h. Okay, now this is just like as if I were trying to calculate f of 3. Right? If this were a 3, right where x was, I would put a 3 here, and I would calculate what that is. It's the same idea, except I'm substituting in something with a variable x plus h. Okay, so the next step maybe is then to distribute the negative 3. And now we're ready to put together the difference quotient. Okay, so the difference quotient takes f of x plus h. This is f of x plus h right here. I'm going to put it in parentheses just so you can keep track of what is what. Then I'm going to subtract the regular function, f of x. In this case, that's the negative 3x plus 1. And I'm going to divide that whole thing by h. Okay, now I always say for these, some nice canceling should happen. So we're going to simplify it as much as we can. What would be the first step? Definitely the distributing this negative, right? So now, since I'm distributing the negative, I'm going to go ahead and take off the parentheses so that I can combine or cancel things together. Here's the nice canceling, right? Notice I have negative 3x and positive 3x. They're going to add to 0. I have positive 1 and negative 1. They're going to add to 0. So I'm left with negative 3h over h. And the h's are going to cancel. So my difference quotient here would be negative 3. Okay, now sometimes the difference quotient will give you a formula so that you can use that formula to calculate the slope of the curve. In this case, because I'm choosing to give you guys just a function that's a line, the line is not really a curve, so we know the slope of the line. It's not a coincidence that we got negative 3, which is also the slope. I do that for you guys in this college algebra class so that you can have a good check to know that you've done it right. You already know what the answer is, which means I am going to be looking for your process, right? So you want to make sure and show all of your steps and work these out so that you can get the difference quotient and get a good idea of how this works. All right, good luck with this. Try some more problems, especially the difference quotient, so you can get a practice and see all that nice canceling happen for yourself. All right, best of luck to you. We'll see you in the next video.